Okay, Assalamualaikum warahmatullahi wabarakatuh. How is everyone? Can you hear my voice?
Yes.
Yes.
Yes, Doctor.
Okay, Alhamdulillah. Okay, so we will now start our class. Thank you for everyone who are here already. We have 28 students, at least 27 in this meeting. Okay. We may have some more people who are not yet here yet. But anyway, we will start our class. And as you know, as I asked in the first meeting, whether you are okay if I do the recording, and you can see clearly that I'm recording this lecture. For those people who object this, may inform me as soon as possible, yeah? All right. Now, so if you read from the agenda, we will be starting our first lecture in this week one, chapter one, about the chemical reaction or reaction engineering one. And the lecture notes will be given to you once I finish my class. Yeah, so you just need to focus listening and also learning from the slides that will be shared during the class. Okay? Yeah.
Okay, Doctor.
So, all right. Thank you, Mr. Afsar. Okay. So I will need to, as usual, my class will start with dua, and it should be the same for any classes for all of you. But in this case, we will initiate it together, and I have shared the dua, the recommended dua that I like, that I really love to share with all my students in the chat room. So normally I will start with doa pembuka, then we will together recite the doa. I tried many times, yeah, but it was never that successful because I'm not sure why. Because maybe you have a problem with your microphones, you don't believe in the power of asking dua from Allah Subhanahu wa Taala. I do not know. Yeah. So in this case, I will still, as usual, initiate it. So I would like all of you to switch on your camera, and you can see the dua from the chat room, and we will recite the dua together. Yeah. That is the only way that we really ask help from God, yeah, when you start learning. So please switch on your camera. Okay, I think you can see your dua from your chat, right? Can you see it?
Yes.
All right, we will start with we will definitely start with doa pembuka. Maybe someone from your class can start with doa pembuka. If you don't know what it means, please ask.
Doa pembuka tu yang mana satu, Doctor?
Ya, apa?
Doa pembuka tu yang mana satu?
Ustaz
Ke doa
Allah
sekali?
Akbar. Contohnya, lepas you habis solat kan, you buka doa macam mana? Mula doa tu.
Saya selalunya baca bahasa Melayu je, Doktor.
Oh,
Doa
bahasa
sendiri.
Melayu je. Doa pembuka, bahasa Inggeris pula. Bahasa Inggeris pun boleh. Siapa yang baca doa dalam bahasa Arab? selalunya doa yang berkat kita buka dengan solawat kepada Rasulullah SAW dulu, dan dah ada tata cara buka doa yang telah diajar ya kepada kita. Apa yang baca doa yang dia buat dalam bahasa Arab? Ada tak? Mungkin you buat tapi you tak perasan tu sebenarnya you buka doa, sebab kamu ni kan diajar ikut je kan. Contoh, Alhamdulillah Rabbil Alamin hamdan yuwafi ni'amahu wa yukafi'u mazidah ya Rabbana lakal hamdu kama yang bagi li jala diwajikal karimi wa azim sultanik. Tu doa pembuka juga tu. Ataupun kalau kamu tak tahu, bukalah doa dengan solawat dulu ataupun Al-Fatihah. Boleh ya? So mana you nak pilih? Yang doa pembuka ni seorang je yang mula dulu. Lepas tu yang doa yang saya share tu kita ramai-ramai angkat tangan dan baca doa bersama-sama. Okay, siapa nak initiate yang doa pembuka tu? Saya ada bagi 3 option tadi. Mana tu? Nak pilih mana? Which one do you want to choose?
Saya rasa Al-Fatihah semua boleh buat serta.
Alhamdulillah. Okay. Right. Mr. Afsar, please lead untuk starting tadi lah. Okay.
Al-Fatihah. Auzubillahi minasyaitonir Bismillahirrahmanirrahim. Al-Fatihah dulu kan.
Amin. Okay, we will start with our doa. We will read it together. Yeah, for the first time, maybe you wanna follow me together. Okay, bukannya lepas saya cakap baru kamu baca, tapi sama-sama dengan saya daripada doa tadi. Okay, nanti the next class, suara yang lagi kuat adalah kamulah, bukan saya. Boleh?
Boleh.
Okay? Alright, Alhamdulillah. So, Bismillahirrahmanirrahim. Sama-sama ya. Allahumma ja'alni fi qalbi nura wa fi lisani nura wa fi basri nura wa fi sam'i nura wa an yamini nura wa an yasari nura wa min fawqi nura wa min tahti nura wa min amami nura wa min khalfi nura waj'alni fi nafsi nura. Lagi satu, Rabbish rahli, lagi satu, Rabbish rahli sadri wa yassirli amri uqdatan min lisani yafqahu qawli. Ada lagi tak doa yang kamu nak baca, yang biasa kamu baca?
Allahumma ftah alaina.
Allahumma ftah alaina hikmataka wa anshur alaina min khaza'ini rahmatika ya arhamar rahimin. Sallallahu alaihi Muhammad wa ala alihi wasallam walhamdulillahi rabbil alamin. Amin. Okay. Thank you so much for your great appreciation for the doa. Alhamdulillah. So it's a very good start for our class today, and I hope that we will do every time when we meet for our class. Please seek doa from Allah. Okay, so now I will start sharing my lecture slide. Hold on a second. Alhamdulillah. Apa yang bersih tu dia lah. Alhamdulillah lu barulah saya jawab. Yarhamkallah. Okay. Can you see my lecture now?
And
Yes.
Right, so this is lecture chapter 1, and I am Amizon Azizan will be, oh no, this is not mass transfer, chemical reaction. we'll be using these two textbooks, Fogler and Levenspiel. And there are also some of the textbook as shown from the first lecture, yeah? And we suggest to use the 5th edition, but most of the reference that I'm using in my lecture today are still in the 4th edition, yeah? I will try my best to see the difference between the 4th edition and the 5th edition. And I'm sure that one of your classmates who have had that 5th edition, who? Siapa tu?
Me, doctor, but just only
Yes.
Oh,
Siapa tu? Ustaz Kasha?
yes.
Right. Yeah, this time I don't open it into laptop, so I cannot see who are talking, you see. So might be next time I will open it into laptops. Baru saya boleh tahu siapa yang bercakap tu. Yeah, so might be if I realize who you are. So we'll go to the next slide. So there is the doa, and we will start right away about our chemical reaction. So you see from this slide the equation of a chemical reaction. So what you can see is you have two components of A and B, which are the reactants producing product C. You can write any names for the reactants and the products. In this case, they are explained that when a reaction occurs, the component itself may lose its identity due to the atomic change or the change in numbers or configuration or the kind, yeah, or the type of configuration, for example, due to also the change in structure or the configurations of the atoms. Yeah. But we also refer to the rule whereby the mass, the total mass, is neither created nor destroyed. Meaning, whatever mass that that enters into your chemical reactor, and those masses, for example, in this case, A and B react with each other, must be in total the same as what produced. Meaning, if you have here 10, then here should also be 10, for example, yeah? We don't give it as a specific unit yet, but this is just to explain that the total mass is neither created or nor destroyed. Involve rate of disappearance of A or B. It means the A may disappear to produce C, the B may as well disappear to produce C. By the end of the day, in your chemical reactor, you may still have some of the A or B which are not converted. And of course, you have the new yield of the new product, which is the C. Yeah. So whichever components which are disappearing, we want to quantify it in terms of rate. How much of A and B being disappeared to produce C? And we can also quantify how much of C being produced per unit of time for both of that. So that is why we use this rate term. Rate of disappearance would refer to the A and B which are disappearing. Yeah, giving you the rate of reaction. Later, in the next slide, you may also learn a new term saying rate of formation, which refers to C. How much time needed to produce C or to form C. So we call it rate of formation, right? Okay, so this is just to say the C is a new form from A and B. So it's a new chemical identity. Now, this slide is explaining to you about the rate of disappearance, why the A and B disappear. Because, well, of course, they react and produce a new identity of C. So what happens when it produces C, when C is formed? The A and B may break and reform. Yeah, the chemical bonds in the A and also in the B may be broken or may be reforming to produce a new chemical bond, which is the new chemical identity of the new product. In this case, C. All right. There are also three kinds of happening in a chemical reaction. It can be due to the decomposition or combination or isomerization. So what are the differences between these three terms? Let us look at the equation here. We have A, which you know already just now. A reacts with B, produces C. In this case, benzene is A, B is propylene, reacts, produces cumene. Yeah, so and you see another symbol here which you call it as reversible. If one arrow only, then we call it irreversible, whereby the reaction goes to one way only and it cannot turn back. In this case, it goes to A plus B A plus B produces C to the left, and the C can reform back to A and B in the other direction. Yeah. What I want to say here is the A and B combines to produce C. Since it is reversible reaction, the C now decomposes and becomes A and B. Right? So we have a combination type and decomposition. And you know, this is a reverse reaction depending on how you write it. Yeah, if you go to your right, it's your forward reaction. Then it turns back to your left, then it's a reverse reaction. So the third type of happening during the chemical reaction due to the losing of the identity of the original identity of the chemicals, which are the reactant, is isomerization. It is neither adds or neither adds other neither adds other molecules nor breaks into smaller molecules. It's just simply a change in configuration. Here, it's either breaking and also combining or adding. But isomerization, it's neither both of that, but it's just simply a change in the configuration. For example, the two isomers, cis-2-pentene and trans-2-pentene. So you have to go back to your organic chemistry, how the pentene are arranged in cis and also in trans. Okay. Now, so take note now, when I show my slide, you can see at the bottom the reference of the contents that I share with you. This is taken from Fogler, and the next slide is taken from Levenspiel. Yeah, you don't have to buy that Levenspiel because we only use some part of it. Yeah, not all. Most of the syllabus for this CHE502 are taken from Fogler, so don't worry, right? Now, what can you see from this slide? What is the difference? What are the new things that you see from this slide? Saya jadi panic queen ke? But anyway, kamu boleh nampak saya ke tidak? Tak kan?
Boleh nampak.
Kalau guna laptop, nampak kan?
Nampak, boleh nampak.
Siapa yang guna handphone tak boleh nampak? Kan?
Tak boleh
Siapa guna
nampak
handphone?
kalau
Siapa guna
pakai
laptop?
phone.
Tak boleh nampak? Okay. Siapa yang guna phone? Saya jadi mannequin je lah. Okay. But anyway, what I want to show you here is, let's say this is the reactor, okay? We'll talk about the design later, but let's say this is the vessel, which you say as a chemical reactor. So you may want to react your two components, A and B. So the A and B must be fed into the reactor. So that is why we have A and B here, which is going to be fed into the reactor as your raw materials. The A and B, the reactants, are your raw materials. Of course, before we do that reaction in the reactor, inside the reactor, the process may need to be undergoing certain processes. For example, physical treatment steps before it enters the real chemical reaction. Yeah. In this case, yeah, of course, it uses the word treatment, whatever. So in this case, let us say it's where you react your A and B. The physical treatment is particularly not for all raw materials, for example. It can be for certain raw materials that need to be pre-treated before it has to be reacted with the other raw material. Pre-treatment, in this case, physical treatment, maybe before sugar to be reacted with microorganism produces alcohol, and that sugar comes from a certain material, natural material. In this case, we call it lignocellulosic material. For example, the trees are lignocellulosic material. It has lots of cellulose, and that cellulose has lots of C's, carbon source. Yeah, the carbon. See, if you write your organic structure, then it has lots of C. It's a complex polysaccharides. So the C are a source of sugar. How to get that sugar before you produce your alcohol, for example? This is what it means by it can be physically treated before to be reacted in the reactor, right? So that is why I say this is not always for all chemical reaction. Then you will see later in the next slide, there are a purely chemical reaction, which, for example, sodium hydroxide with hydrogen, something like that. If you have chemical reaction, and that sodium hydroxide, in real situation, you may just simply buy from the company supplier, the chemical supplier. But let's say if you don't have that sodium hydroxide, you want to produce your own sodium hydroxide. So you may want to go through with a few steps before the reaction. Okay. And finally, that product coming out from that reactor may also need to undergo certain treatment. For example, if you were to separate the main product from the byproduct, so finally that would be your main product that you want to sell to the market. So this is just to show you the typical chemical processes. This is very layman, but the details inside this are your design project assignment later when you are in part 7 and 8. But before that, in part 5, you already learned you will learn your mini project in your design project course, for example. Yeah, but here we already introduce it in your chemical reaction, in chemical reaction engineering class, so that you can already foresee whatever principles that you learn in reaction engineering, theories and equations are actually to be used in your design, yeah, in your later years. Now, when you do your production, when you want to get your C, you also need to think about the economic analysis. So in this case, the money, the cost, despite considering what happens in the reactor itself. Of course, this is reaction engineering, but what happens in this reactor relates to many principles that you may have learned from other courses. For example, the heat transfer. Why? Because when you want to react A plus B to produce C, it can produce as much as C at a specific temperature, for example. So you need to know at which operating temperature that is most optimized or suitable. I like to use the word optimize because it means the optimization of temperature in that reactor means how maximum C can reach with the specific temperature. So it means optimized temperature. So it is either how hot or cold of transfer, meaning let's say if the reaction release energy but the optimized temperature is colder, then the temperature inside the reactor increases, but the temperature must be lower. So you need to control the temperature inside the reactor. Yeah. In this case, you will need to learn you will need to apply your heat transfer principle like Newton's law of cooling or Fourier's law. If I ask you, I'm not sure whether you still remember, you know what Fourier's law is? Saya jadi mannequin lagi. Newton's law of cooling, radiation, heat transfer dah belajar belum? Semester berapa?
Semester lepas, Doktor.
Baku lagi. Memanglah pandai ni. Semua dapat A dah. Okay, basically those are the examples of laws. What I like to tell you here is, let's say if you want to control that temperature to 30 degrees C. Oh, ni rendah sangat. Let's say kalau pure chemical reaction sampai 400 degrees C lah katakan. Okay. So you need to set the temperature to 400 degrees C. How would you do that? So you need to heat up the reactor so that the reaction mixture will reach that temperature, 400 degrees C, for example, or 30 degrees C, for example. Okay, paling senang, if you want the temperature to be constant, T constant, remember the word that we use, isothermal, right? In the first lecture, T constant, let's say 30 degrees C, but during that reaction, it releases energy and the temperature increases to 60 degrees C. So how would you allow constant temperature of your reaction mixture in your reactor? How would you do that? Kita nak apply heat transfer ni. Walaupun dalam chemical reaction in reactor. Inilah kerja kamu ni. How would you do that?
Use a coolant.
Use coolant. Very good. So how would you supply coolant?
How would you apply coolant?
Huh? Dia?
Not sure.
Huh? Tak dengar. One of the way is you have certain cooling outside the reactor. If the temperature difference is not so high, ni dah masuk kelas heat exchanger lah pula kan. Or you can control your temperature, yeah, heating or cooling for the pipeline before it enters. Tapi now kalau berlaku kat dalam, so you have to cool down the whole reactor. One of the way yang selalu, which you always see in the industry is we have a jacketed vessel. That is one way. So how to, if the heat transfer or the temperature change, delta T is not so high, maybe in that jacket, we simply use water that absorbs the heat from the reactor. You know heat transfer, bila ada heat, dia akan transfer the heat to the vessel thickness. Vessel thickness katakan glass ataupun stainless steel. And each of this material ada apa? Ni yang kita guna Fourier's law ni. Ada apa? Ada constant conductivity. Alright? And due to that conductivity, the heat will be absorbed by the heat release in the reaction mixture. and that temperature, surface of that stainless steel inside, if you assume not much resistance, akan sama outside. So you read the temperature outside will be assumed to be the same as temperature inside. But you know it needs to be 30. But now it shows 60. Alarming. So what should we do? So this is where you control the temperature by, ni lah kamu design lah macam mana nak control temperature tu. If you use jacketed, water jacketed, then the water will absorb the heat until dia baca 30 degrees C. Something like that. So that is a very simple industrial application. You may also do that in your mass and heat lab. Is that this semester?
Yes.
Unfortunately, you tak pergi lab kan? So please take the opportunity to always imagine how to do that in real life. Because when you are not without ODL, you can go to the lab in pilot plant and see the heat exchanger and test your heat exchanger, how to control the temperature. So this is very important, yeah? If we don't control the temperature by using the heat transfer principle, your job is to design the specific heat transfer application to control the temperature in the chemical reactor. Bukan kerja orang lain, ni kerja chemical engineer. Right? Of course, in this class, you learn about the chemical kinetics. Why we want to talk about how fast things happen? Because we want to produce as much as possible, as much yield and as fast yield as possible, because we are talking about money, right? In this reactor also, you apply the thermodynamics, the first and second and third laws, which you have learned in your, Master 1, thermodynamics.
Second
Right?
semester.
Diploma. Lagi lah hebat. Diploma belajar. Second semester pun belajar juga. Chemical Engineering Thermodynamics ya?
Di SEM ada.
Oh, di SEM.
SEM ada juga.
Dia ada juga. Chemical Engineering Thermodynamics ya?
Ya, doktor.
Very good. So you also will apply fluid mechanics in your reactor. And of course, the mass transfer in your reactor. So how to relate this mass transfer? It is simply the mass, how much mass is being diffused. Let's say from liquid to solid. If you have some other solid inside, yeah, if you have some other solid, yeah, you have liquid, you have solid, and liquid reacts with solid, and how the reaction occurs due to mass transfer to produce a new product. So this is what you learned last semester. One of the example of the law is fixed diffusion law. All right. Of course, you test it in a small scale, but for the production which you want to sell in a mass bulk volume, you will need to know later on how to do scaling up. Yeah. Let's say, for example, this is just 10 liter ataupun 1 meter cube. Okay. 1 meter cube, 1 cubic meter is equivalent to how much liter? 1 cubic meter is equivalent to how much liter?
1,000 liter.
Correct. Let's say this reactor is 1 cubic meter. The scale up would be nak buat sampai 10 cubic meter. So it will mean scaling up. Yeah. So you will also need to do that one day. But in this class, we don't teach you scale up. Right? I think you will learn that in plant design, if I'm not mistaken. So the output will be a function of input. The input would refer to your reactant. The kinetics would refer to whatever happens inside your reactor, the chemical kinetics. And contacting would be, in the next slide, I will show you the contacting would be types of flow that you may use, yeah, for your chemical reactor. Yeah? Let us start with this slide. showing you the basic chemical reactor. You have this reactor, you have input, the reactants, you have your output. Of course, the contacting pattern is what happens inside the reactor. The components react with each other in contact with each other, whether it can be clumping or at a state of aggregation, or they are all liquids. There are contacts between liquid and solid. You have to already ask those questions. Yang you nak react ni, components that you want to react to produce your marketed product, dalam fasa apa? In which phase? Liquid, gas, solid, or everything in there. Yeah, so those are the things that you need to know, the contacting pattern in your reactor. Of course, finally, you want to learn about the kinetics of those different components reacting in your reactor. Okay, so the kinetics would mean how fast things happen. If very fast, then equilibrium tells what will leave the reactor, meaning whatever leave the reactor would refer to the output. And that output can be a mixture of your main product and your byproduct. Okay, so this reactor needs to be designed by chemical engineer. Who would explain the kinetics in the reactor with your specific design reactor? You. So the kinetics and pattern in the reactor. Who will talk about all those things? Also you. Yeah? All right. Now, so there are three kinds of flow. Take note of this term, steady state, and also unsteady state. Any occurrence start with unsteady state. Then when it reach its equilibrium, then you say it's steady state, something like that. So there are three kinds of flow. It's either batch, plug flow, or mixed flow, right? Since you are in ODL, if you are not, you may have the opportunity to be in the lab to see batch reactor, plug flow reactor, and mixed flow. It's just something that you mix. Yeah, this is, of course, this is reactor as well. Now, the batch would mean whatever that you put in as your reactor, input in your reactor, just stay there, leave it reacts. Then at one time, you just extract. Yeah. So there is no continuous flow. Continuous flow of inlet and continuous flow of outlet. No. So this is what we call as batch. Plug flow is simply the fluid that flows in the pipe, then leaves the pipe. All right. The fluid passes through the reactor with no mixing of earlier and later entering fluid, with no overtaking, and if the fluid moves in a single file through the reactor. So this is plug flow. You did that as well in your last semester's lab. Of course, lah. So mixed flow is uniformly mixed, same composition everywhere within the reactor and at the exit. So this is simply mixing in the reactor. Of course, there are some reactions as well. All right. Now, in this class, you will need to know how to differentiate between the reactions that are in the reactor based on the order of reactions, based on the classification of reactions. Can be either homogeneous or heterogeneous. Can be exothermic or endothermic, reversible or irreversible. We will look into the details in the next slide. And the order of reaction can be classified based on molecularity. Then we have to know how the reaction equations are written. Then we can write the order of reaction. Whether the reaction is elementary or non-elementary. Whether we have one single reaction or we have multiple reactions to get to your final main product, right? And that multiple reaction may be whether it's in series or in parallel type of reactions. Yeah, we'll look into that one by one. Now, so the keywords for this class is single phase, multiple phase, other than the single reactions and the multiple reactions. We have reactant, we have product, it's either reversible or irreversible. And the reactions occur in an ideal reactor or sometimes it becomes non-ideal. Yeah? So those are the things that you have to bear in mind. Then this is just an extra note relating to reversible. Yeah, why the reaction reverse to the different direction? It produces C from A and B, then C decomposes to produce back A and B. Why? And what are the parameters which influence that reverse reaction? So one of it is concentration of the both reactants and also the products may influence the reverse and forward reaction relative to the corresponding equilibrium concentration. You will see that later. This is just a basic thing, just to show you the rate of reaction type from very slow to very fast. Okay, you can see here cellular reaction can be very slow, but bimolecular reaction can be very fast, or rocket engines or jet engines. Okay. Now, when we talk about jet engines or rocket engine, so I love to talk about this SN11. Yeah, we will do that someday. Yeah, all right. Now, let us look into the classification of chemical reactions in a reactor design. So it can be homogeneous and heterogeneous. Homogeneous means only one phase, yeah? Heterogeneous, maybe you have liquid and gas together or gas and solid together. So at least two phases. So those are the examples of the homogeneous and also the heterogeneous reaction. And look at the keyword here, non-catalytic and also catalytic. Non-catalytic means it has no catalyst, but catalytic with the catalyst. If your catalyst is solid, in your liquid reaction, it is still considered as heterogeneous reactor or reactions because we have two phases. And those are the few examples like the synthesis of ammonia or the oxidation of ammonia to produce nitric acid. So it may have some catalysts here, different kinds of catalysts which allow fast kinetics or fast chemical reaction. All right. Now, so let us look at this example. This is just an exercise, which is which, homogeneous or heterogeneous. Let us look at one by one. Knox formation. Is this homogeneous or heterogeneous?
Homogeneous.
Correct, because we have those all in the same phase. Yes. Second one, ethylene production.
Also homogeneous.
Yes. So the G refers to gas. The third one, cold combustion.
Heterogeneous.
Heterogeneous. So this is solid with the gas. See the carbon and also the oxygen producing carbon dioxide. Heterogeneous. And the last one, sulfuric acid.
Homogeneous.
This is homogeneous. All right, very easy. So reaction rate can be written in many forms. Yeah, have a look at this based on unit volume of reactant stream. So I would rather not read this written form, but I would go straight to the formula. R refers to reaction rate. I refers to whatever component. Okay. Then we have R without the prime, R prime, 1 prime, R double prime, R triple prime, R quadruple prime. Prime to apostrophe lah. Okay. So reaction rate is always based on how much moles of that I form. How much moles of that I form, that I component per unit volume, per unit time. The second one is per unit mass weight of the solid per unit time. The third one is per unit surface. Can be how much surface can be. The third one is the interfacial surface, normally in centimeter squared or meter squared per unit time. Per unit volume of the solid, in this case per unit volume of the fluid, this one per unit volume of the solid, and this one per unit volume of the reactor. So all of them would refer to how much moles of new component produced per unit volume per unit time, right? Now, we'll look into the units later on, somewhere here. It's just going forward, but we'll do into that in detail. Now, let us look at the exothermic and endothermic. Exothermic is simply the energy which is being released to the surrounding as heat. Therefore, the temperature of the surrounding increases. More energy is released when the bonds are formed in the products that is used to break the bonds in the reactant. Right? Meaning more energy released when bonds are formed in the products. Meaning you produce C, energy releases more than used to break the bonds. Endothermic is the reverse. The heat which is absorbed from the surrounding. The temperature of the surrounding drops because the heat is absorbed from the system. More energy is absorbed when the bonds in the reactants are broken. Yeah, the reactants of course broken, but it absorbs the energy. Yeah? Endothermic reaction. Then it's released when the new bonds are formed in the product. Right? Now, reversible and irreversible. Irreversible, one direction. Reversible, you have forward, you have reverse. Right? This is irreversible, only one way. This is irreversible. Go to your right, go to your left. The example would be this production of silver chloride from silver nitrate. So once you produce silver chloride, you can never go back to silver nitrate. But here, once you produce ammonia, can still go back and produce back the nitrogen and hydrogen. So this is the latest energy that we have in the world. Yeah, the current trend of energy, which is the hydrogen, either the hydrogen energy or the ammonia energy. Ammonia is the most latest trend of the future energy of the world. But the current trend existing already being applied in Europe, but not so much in Malaysia. I don't think so in Malaysia, is the hydrogen energy. So this is one of the ways to produce hydrogen from ammonia. So if you have any reaction producing ammonia, so you can break the ammonia, becomes hydrogen, and you can use this hydrogen as your source of energy, which can be used in your car, in vehicles. So in Europe, the hydrogen is already used in train or buses. Yeah. Of course, in Malaysia, we don't go for that hydrogen energy yet because we have so much of this petroleum and gas, right? But this is just to tell you the current trend. If you were to work somewhere in Europe once you graduate, of course, you will have this experience of taking a bus with the hydrogen gas, thing like that. So those are the other examples of the reversible reaction. Now, we are going to talk about, ada 1 minit lagi pada pukul 11. You want to take a break?
Yes, Doctor.
5 minit?
Yeah, that will be sufficient.
Okay, thank you. So we'll just take our first break, okay?
patient je.
Yang buku kan.
Mm-mm.
Tapi beli foto state pun senang juga.
Ada 2 patient. So tak nipis, tak tebal. Dia percaya.
Masa
Hello, Assalamualaikum. So we are back here. Can you see me?
Can.
All right, you can still see the slide, right?
Yes, doctor.
All right, so we are now in slide number 19. We are going to proceed with the single phase reaction. This is a single phase reaction, assuming this is only one phase. So what we want to see here is we have this A and B producing R and S. You can also write as C and D as your products. Before that, you see as A and B producing only C. But here, we just want to add, for simply of learning the stoichiometric coefficients. So we add another product, which is D. Now, what you see, the alphabet, which is shown in green color, are the stoichiometric coefficients. We call it coefficients. In other words, what you have known earlier, whatever moles of A reacts with whatever moles of B, producing whatever moles of R and S, or whatever moles of C and D. Yeah? How many moles of the A, B, R, S, or A, B, C, D? And those moles, as what in this course we call it as coefficient, the stoichiometric coefficients. Basically, the reaction would have a balanced stoichiometry. Yeah? So this is what you're going to be applying when you do your material balance or your mass balance for your equations. All right? Of course, you know the A and B are the reactions, the C and D are the products. Now, we're going to go back to our symbol R, which means the rate of reaction. If you see negative means the rate of disappearance. What are disappearing? The A and the B are disappearing. So if you want to write the rate of disappearance, you use negative. Rate of reaction of what? Based on, let's say if you choose A, yeah? So rate of disappearance of A. In English, you say rate of disappearance of A, but you write it as negative RA. If you want to write rate of disappearance of B, then you write negative RB. The subscript, okay, not as the same alphabet level with the R. The subscript. Then we have negative of 1 over per unit volume per unit time. Remember the units, the definition of the rate of reaction per unit volume, meter cube or cubic meter per unit time. The chosen time is a second. And how much moles of A disappearing, because you are referring to the rate of disappearance of A. All right. So the other words, we also call it as rate of disappearance, or if you can also write as rate of formation of R, or rate of formation of S, or rate of generation. Can also do that. Now, the second equation would show you the relative rate of reaction. Yeah, so we have here A, B, R, S. So minus RA relates, means rate of disappearance of A. The relative rates means per A is equivalent to negative RB per B. B, those are the stoichiometric coefficients for the A and also the B. Yeah, the small A and B refers to the stoichiometric coefficients for respective components, reactants A and B. Right? Same goes to the rate of formation. So take note, the rate of formation, you don't use a negative sign, but you use a positive sign because it refers to the rate of formation. Right. Now, the rate of reaction depends on the concentration and temperature. And they are also influenced by the composition, which also means concentration, and also energy, which refers to temperature of the material. So in other words, we can write the rate of reaction is in the function of concentration and temperature. The rate of reaction is independent. Independent means it is not depending on the type of reactor. Doesn't matter which type of reactor. It doesn't change the rate of reaction. It only the parameters that change or influence your rate of reaction or how fast your products are being produced, only the concentration or the temperature, but not plug flow ke, batch flow ke, continuous flow ke, stirred tank reactor ke. No, it does not depend on that, right? It depends on the concentration of your reactants. If it's reversible, also the concentration of your product so that it can go back to the reverse reaction, and also the temperature of your reaction. Now, so this is the same thing as what you see earlier. The rate of disappearance depends on the temperature and also the concentration. Due to that, we can write the temperature dependent terms and the concentration dependent terms. The rate of disappearance, since we have negative here, can be also written as this equation. So this is the main equation that we're going to learn today, based on the K, which is the rate constant, times C is normally concentration. Concentration of what? If you have the subscript A, then concentration of the A to the power of small a. And that small a, remember, is the stoichiometric coefficient for the component A to the power, okay? So it depends on the mole, yeah, of your A. C to the power of A. C of A, concentration of A to the power of the stoichiometric coefficient. And this main equation is can also be written based on the Arrhenius equation. Here, it depends on the concentration. Look at the equation. It has the concentration. Here, of course, we have the concentration as well. But the K here, which is the rate constant, can be written in terms of activation energy and also the ideal gas law constant. Meaning, this K is equivalent to this K naught exponent to the power of minus E over RT. And those are the Arrhenius equation. Times the C, the concentration of A to the power of the stoichiometric coefficient of the component A. So take note of the units here. You'll see that clearer here. The K is the reaction rate constant. For this case, for this equation, the rate constant is 1 over second. But later when we have an exercise, the rate constant may change, yeah, based on different scenarios. Either, you will see that in the next slide. Then the K naught from the Arrhenius equation is the pre-exponential factor. The N is the order of reaction. Where is N? Actually, this is referring to the total order of reaction. It's actually the A as well, reaction order. So it's the same thing. The N would refer to overall. The E is the activation energy. The R is the ideal gas law constant. So I just write the unit for R. Absolute temperature in Kelvin. Then concentration of the A. Of course, please remember the unit for the concentration. We are talking about moles of A being formed or moles of C being produced. C produced, A disappears. Sorry. So concentration of A disappears. So the unit is always how much mole of A per unit volume, right? Okay, so those are the stoichiometric coefficients. Now, the concentration may depend on it's either single or multiple reaction, elementary or non-elementary. When we assume for a concentration dependent term, when you make that assumption, we want to make that assumption at a specific temperature, yeah, at a constant temperature. Here, this is an example of a single reaction. See, only one reaction producing R, or in this case, hydrogen bromide from hydrogen and also bromine. Here, you see multiple reaction. And that multiple reaction can be either in series or in parallel or complicated scheme. Now, let us look at one by one. Series means what? The A produces R. After you produce R, then only S is produced. So the S cannot be produced directly from the A. It has to go through the R first. So the A to R, R to S. So this is series. Parallel means same A, at the same time it produces R and also S. And they are competing with each other. A to R, A to S at the same time, right? There is one example of parallel. The second example of parallel could be they are side by side. The A produces R, the B produces S. So we have two parallel equations. Complicated equation. The A plus B produces R. With the R, reacts with the B, produces S. Maybe in this case, it's complicated. You have A and B, but finally, what you want is not R. What you want is S. But you have to go through these two equations. Yeah, the first one, series one with respect to A and R. A to R. Series two with respect to R and S. R to S. Okay? Now, let us look at the definition of elementary. Elementary apa pula? It depends on the stoichiometric of the equation. So that is elementary. How? For example, if you look at this equation, A reacts with B, produces R. So this is a single reaction and also elementary. Why? Now we look at the rate of reaction equation. Minus means rate of disappearance of the component A. Then we have the rate constant, and it depends on and that rate constant depends on the temperature. Remember the Arrhenius equation? Yeah, we have the absolute temperature and so on, times the concentration term. And since we have two components, so we multiply both the concentration of A times the concentration of B. Then remember, from our previous slide, we have this A, yeah? A, the order, the reaction order. And that A is actually the stoichiometric coefficient, right? Here, if you look here, go back to this equation, CA to the power of 1, CB to the power of 1. And that 1 is actually A here, that is actually B, which is A and B. And you see from this equation, it's actually 1 mole reacts with 1 mole of A reacts with 1 mole of B, producing 1 mole of C. So this is what we say as it is referring to the stoichiometric equation. Whatever value of your stoichiometric is actually shown by your reaction. Yeah, 1, 1. Okay, that is easy. Later you will read this extra information that I give you. Yeah. So this is what we say as it depends on the molecularity plus the rate constant of the equation. So you have A and B, yeah, and the 8th order with respect to A, the B order with respect to B, the N order with respect to overall. Overall means the A and B, A plus B, giving you the overall order of reaction. And take note, the A and B can also be fractional, meaning pecahan. Okay. Now, what is non-elementary? Just now, it is elementary. Non-elementary is the opposite, meaning it does not depend on the stoichiometric. For example, here, does not depend on the stoichiometric equation. For example, this is one of the first example, positive, yeah? Rate of formation of hydrogen bromide. By right, patutnya you letaklah C hydrogen bromide to the power of 2, right? Because the stoichiometric equation is 2. But in this case, from the experiment, it doesn't follow the elementary rule. Yeah, the formation of hydrogen bromide does not follow the elementary rule. The elementary rule means uh, whatever power value a b to the power of Ca to the power of whatever, Cb to the power of whatever, follows the stoichiometric coefficient. That is elementary. But when it does not follow the stoichiometric coefficient, then we call it non-elementary. How do you know? Of course, from experiments. Yeah, you don't know it by guessing. Whatever that we have here, this conclusion comes from experiments in the lab. Yeah, proven theories. In this case, chemists found that some of the reaction can be non-elementary. They call it non-elementary because the rate of formation of hydrogen bromide is as such. Ada ratio pula bawah ni. Right? To the power of half. Where half? Stoichiometric coefficient. We don't see any stoichiometric coefficient of half there. Right? Okay, so back to the definition of non-elementary means simply when the reaction order are not identical to the stoichiometric coefficient of at least some or not all of the reacting species of the reaction. For example here, okay, this is much a clearer example of non-elementary. So we have A here, B and C. So you know this A is 1, B is 1, C is 1. If it is elementary, then the C, the concentration of the CO must be 1. Of course, this is 1, correct, elementary. But the second reactant, the chloride, is not 1, even though the stoichiometric is 1. So when either one of it not elementary, then the whole thing can be said as non-elementary reaction. So this is what defined here, yeah? Not following the elementary rate law when reaction orders are not identical with the stoichiometric equation of at least some or not all. Okay? Or all. Yeah, not following. Yeah? Okay. Examples of elementary. This is easy. A produces R. Rate constant. Since this is only one reaction, irreversible, so only one K we have. If it's reversible, then we have one to the right, we have one to the left. So the rate constant will have two kinds. So we can say to your right is K1, to your left is K2. We can write that. But this is irreversible, so we write it as K1, yeah? Only one direction. And the rate of disappearance of the A is equivalent to the K1, which refers to the rate constant times to the concentration to the power of the coefficient, which is 1. This case 1. So it's elementary. The second elementary here, okay, we have another scenario. Even though we have 2 moles producing 2 moles, then we still write it as such. Yeah. So it is elementary equation. K1 times Ca to the power of 1. In this case, even though, okay, I forgot to mention here in the previous slide, since we have A is equivalent to 1, right? And we only have A, we don't have another C, we don't have that, another C, we don't have that. Why? Because we only have one reactant. So the total order of reaction is simply A. And since A is 1, so we call it first order of reaction, right? For this case, even though we have 2 moles of A producing 2 moles R, of course, you may write A equals to 2, right? Even though 2, you cannot simply, okay, it's actually A and R. No. So we call it second order equation, yeah, for this case. Here we have B, 1 mole of B reacts with 2 moles of D, produces 3 moles of T. So how do we write the rate of disappearance of B? Negative RB. Is simply the KB, the K, the rate constant with respect to B, times, since we have two components, so concentration of B times concentration of D. The stoichiometric for B is 1, so to the power of 1, but here 2 to the power of 2. Okay, if you write the rate of disappearance of D, the same thing. Rate constant KD, so the concentration of B to the power of 1 times concentration of D to the power of 2 remains the same. But how you write it is rate is measured in terms of reactant D. Here, since we have subscript B, in terms of reactant B. Here, we have positive, it means rate of appearance or rate of formation. You still write the same thing, yeah? So KT, rate constant based on T times C of the B, C of the D to the power of 2, right? Simply what differs is the positive sign. Now, for stoichiometry, if you want to make a relationship between the RD and the RT, for this case, or that is the simplified equation after considering this equation, yeah? So minus RB is equivalent to minus half of the RD, is equivalent to 1/3 of the RT. Right? Then you can simply simplify that by KB is equivalent to half of the KD is equivalent to the 1/3 of the KT. Now, we have only few. Banyak juga ah. Oh no, pula saya bercakap saya banyak punya slide. Dah setengah dah. Can you still go on? Ataupun laju?
Can.
And not so difficult, right? If you focus, then not so difficult. Now, we want to look into non-elementary equation. Why is it said non-elementary? Because we know that it does not follow the stoichiometric rule, the stoichiometric coefficient. Now, we have 1 mole of nitrogen reacts with 3 mole of hydrogen, produces 2 mole of ammonia. The rate of formation of the ammonia is as such equation minus such equation. That is an example of non-elementary equation. So this is another example of non-elementary equation. We have a series of reactions. So we call it multiple reaction. Reversible lagi. Your final product sebenarnya what you want is AB from A2, right? That is just a symbol, the symbol that used, very basic one. A2 produces 2 mole of A, and then we have A star. A star here, whatever A star, whatever star, refers to intermediate. Intermediate means in between. Why we say in between? Because your main product is actually AB. This is what you want. This is what you want to sell from your main reactant, A2. But it goes through many reactions. And that from many reactions, it has many new components which are not used, disappears in between. Yeah, what you see finally is AB, but in between, it produces B star, it produces A star. So what happens to A star? A star reacts with B2, reversible producing AB, and reacts with and produces B star. This is again another intermediate. Why we call it intermediate? It's in between the third reaction. So we have two kinds of intermediate. The last reaction has the intermediates reacts with the intermediate. Finally, then only it produces your AB. So this is a series of elementary steps to explain the kinetics of the non-elementary reactions. Okay. So we have also another term, new terms that you have to bear in mind, where you will learn more of that in your reaction engineering too, which is non-chain and chain reaction. Right? then this is just fundamental theories, yeah. The intermediates can be in the form of free radicals or polar or ionic substance, can be complexes, it can be molecules, yeah, reactive intermediates. Yeah, so this is what I said, intermediates, 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 and this is your final product, AB. And this is an example of a reversible chain reaction. So let us look at the definition of chain and non-chain reaction. Now, the previous slide shows you the chain reaction. So what is chain reaction? Chain reaction, because we have three kinds of reaction. This is what you're going to learn in your reaction 2, but I'm just telling you as basic. Reactant produces intermediate, and the intermediate reacts with another reactant, producing another intermediate in propagation level. The first one is just initiation. Without the initiation, you will not get your propagation level. With the last level, the last reaction is the termination. That is where it stops to produce your product based on your reaction between the intermediates. So that is chain. Non-chain is reactants produces intermediates, and intermediates finally directly produce product, right? So that is non-chain. So remember, you will learn this in your CE2. Basically, this is an overall introduction. Let us look back at our Arrhenius law. Always remember, your Arrhenius law is simply that equation, which is the temperature-dependent term for the rate constant, right? So now we see another new symbol, which is K naught, and E, of course, you have seen it earlier, R and T. So what are those? The E is the activation energy. R, of course, you have seen this. T, absolute temperature. The K naught is the pre-exponential factor, right? So please apply this Arrhenius law when you want to explain about your temperature-dependent term. Now, examples of molecularity, either three or molecular reactions. So we have three species. By molecular reaction, we have two species, and unimolecular reaction, we only have one species, but it produces another species simply by rearrangement of a single molecule to produce another molecule. A to B or A to B or C. So that is unimolecular reaction. Normally in a radioactive decay, for example, here uranium-238 produces thorium and also helium. Okay. Now, this slide shows you how to write the relative rates. Of course, this is basic. The relative rates depends on you are referring to what. Let's say if you are referring to A, right? So let us just read this one first. It means for every mole of A, because you are referring to A. For every mole of A disappears, how many moles of C produce, form, or D form? How many moles of C form or how many moles of D form? Or you can also say how much is needed for B, how much B is needed for every mole of A. So this is what we say as relative. Relatively comparing to what? So how to do that? We still have the A plus B produces C plus D. So if we refer that to how much, refer that to A, then the stoichiometric A divides by A. Yeah, every stoichiometric divides by A. So that will give your relative rates of reaction. So now we're gonna look into the basic that you have seen earlier. It has its name, so we call it power law model. Why? Because we have this power to the power of alpha to the power of beta, or the stoichiometry. and also multiplication. So it's a power law model with the K and also the concentration. The overall order would mean the total order of the stoichiometric coefficient in the concentration species, right? Now we have three kinds of law, either zero law, first law, or second law. Let us look at the zero law. Zero law means this is rate of disappearance of A. Then if we are referring to concentration of A, then the stoichiometric, salah, sekejap, I want to erase that one. So basically, we may have this equation, alamak, tak boleh tulis. We may have this, oh, okay. We may have, I cannot tulis. Hold on. Dia tak bagi I tulis. Dah boleh. So we may have this C species, let's say A, to the power of A, the stoichiometric coefficient. In this case, the A, okay, tulis. The A is now 0. So whatever C, whatever number to the power of 0 is apa? 1.
One.
So
One.
that's right. 1 multiplies by K, then it will give you the rate of disappearance of A is equivalent to only the rate constant. Right? So we call it zero order. If it's first order, the A is 1. So this is first order. Tak ada pula B kat sini kan? Tak ada. Because only one species. The unimolecular. Only one species. So tak ada. So this is first order. If it's second order, then we have this A is 2. Tak ada pula yang lain. Alright, if you have another species, then of course you have to add it at the total order of the reaction. Now, I will need to go back. Now we want to determine what is the unit of this K and what is the unit for this R.
Second.
Apa yang sebut tu tak dengar. What is the unit for the rate of disappearance? Mole per unit.
Volume per
Yes,
unit.
per unit volume, per unit time. Okay. Now, let's say if you use dm, yeah? dm is cubic decimeter. Right? In this case, I forgot to stress it here. Ada echo ke?
Tak ada.
Tak ada. Okay. The unit for R is how much mole of that species per unit cubic decimeter per unit second. Right? For those people who have seen, who only see this for the first time, cubic decimeter means it's a metric unit of a capacity, of course, a capacity, volume, defined as volume of 1 kilogram of pure water under standard condition. A volume of 1 kilogram of water under standard condition. So that's why we write as cubic decimeter. This is cubic decimeter. If it's a zero order, what would be the unit for the rate constant?
Mole decimeter second.
Yeah, it's the same thing, right? It's the same thing. Mole per cubic decimeter per unit time. What about this one? This is still mole per decimeter time. What is the unit for concentration?
Mole per volume.
Mole per,
Decimeter cube.
that's right. So what is the unit for the rate constant?
S minus 1.
1/s.
That's
1 over
1
S.
over second. Okay, that is first order. What about second order? So this is mole per dm cube per unit second. What is this unit? Ca squared. What is the unit for Ca? The unit for Ca is mole per dm cube, right? If you have two, what? Then mole is twice that. Dua kali lah you tulis. Betul?
Dot.
Tak When I merajuk. Tak lah when I. Tak tahu. Table. Itu ada. Jahat lah. So, I tulis tangan lah. Mole is more per. Tulis tangan susah lah. dm cube. So, tell me what is the unit for K?
dm cube
dm
per
cube.
mole dot second.
Yes.
M cube per mole per second. Very good. Excellent. So, I cannot write. Dah boleh lah. So, hold on. Kita tulis ya. Right. So, this is... tak pergi balik. Jahat loh. Jahat betul lah. Sekejap. Dia bagi, dia tak bagi lah. Whatever. So, you already know ah. So, these are the summary of the rate constant unit with different rate laws. Dia bagi pula. Alright. For zero order, for first order, for second order. We did that until second order, right? So you can also do that for the third order. So just do that and you can determine the unit for the rate constant. So what can you say about this lesson? Does the rate constant stay the same for all kinds of reaction? The unit, I mean,
No.
unit.
No.
The unit, always remember when you write the unit for the rate constant, it depends either it's zero order, first order, or second order, or third order, or etc. Right? Order nak buat breakout room, tapi nak habis dah masa, tak apa, it's okay. Now, I just want to show off examples of the elementary rate law. So again, you know, this is the rate of disappearance of nitrogen oxide to the power of 2, of course, to the power of 1, to the power of 1, to the power of 1, right? And my last activity is that I want you to actually be in your room, but we can do that later. And but the activity is to divide you in a random group. In teams, we can divide that randomly. Then you will need to go to your friends' views on the first flip grid on the chemical reaction and relate it to what you learned today. But since we don't have that much time to do that, I underestimate my teaching style. I thought I can do that in 1 hour, but always make it more. So I am going to do that in the next lecture because we have some more points that I need to show you on examples of the non-elementary. And we will need to try that as a breakout room because I want you to discuss with your group members randomly, which I will divide it automatically by using Teams. Then you look at your friends' views and choose which views that you want to elaborate on the principle of rate of reaction today. Because I've seen, I've heard your videos, some have been presented, I mean, in terms of points, showing that you already have this basic chemical reaction, but we want to relate it in terms of first order or second order or third order or whatever, elementary or non-elementary, right? With multiple phases or a single phase, or can be multiple reactions or only one reaction. So maybe a little bit of digging of more information on what is the particular examples that you mentioned during your first flip grid assignment. Okay, so we'll do that in the next meeting, and I hope that you have great weekends this week, because this is our last meeting for the CHE 502 in first week, and we'll see you again next week on Monday. Is that correct? Monday, right?
Betul.
Yes.
Ya.
Kejap nah. Saya nak tunjuk muka saya lah. Stop sharing. Dah nampak muka saya? Dah stop sharing kan?
Dah nampak dah.
Alright. So are you still there?
Yes.
Nampak semua?
Ada.
Yes.
So hari ni ada siapa-siapa tertidur tak?
Tak ada.
Tak ada. Okay,
Masih segar.
bye-bye. Assalamualaikum. Masih segar Nak ke lagi? Boleh ke? Lagi. Masih segar kata, jomlah. Sambung lagi setengah jam. Alright. So have a nice weekend and we'll see you again next week. Yeah. Assalamualaikum warahmatullahi wabarakatuh. Thank you for your cooperation.
Waalaikumsalam.
Thank you,
Thanks,
Doktor.
Thank you so much,
Doktor.
Doctor.
Thank you,
Welcome,
Doktor. Bye-bye.
Bye.
Ada student jawab. Tak nampak.